Hi, now we are analyzing CSIR June 2011 Chemical Sciences. Just a look at the given problem. In a chemical reaction, A, B are in equilibrium with C. So where A is a solid and the reactant B is gas, the product C is also gas. Okay, the total pressure at equilibrium is 6 atmospheric pressure. The value of equilibrium constant is, so here the hint is the total pressure, that is 6, and at equilibrium the pressure of reactant B must be equal to the pressure of product C. Okay, then only the total pressure will become 6. Okay, right, and by that logic, now the equilibrium constant equals to the pressure of the product by pressure of the reactants. From that, answer will be 1. So third option is the correct answer for given problem. Next one, a molecule AX has a vibration energy of 1000 and rotational energy of 10 centimeter inwards. Another molecule BX has a vibration energy of 400 and rotational energy of 40 centimeter inwards. Which one of the following statement about the coupling of vibrational and rotational motion is true? So here we have given with different combinations as options. The correct answer is, whenever we look at the given data, the energy of AX, that is of vibrational energy, as 1000 and rotational energy is 10 for AX molecule, and for BX type the energy as 400 and rotational energy as vibration energy as 400 and rotational energy as 40. Now just look at the differences of those energies of AX and BX, and from this concept, that is energy difference of two motions inversely relates with coupling. Okay, right, and if you look at the second one, the BX type molecule, whereas the energy difference of the two motions is less when we compared with energy difference of the first molecule, that is AX. Okay, so whenever energy difference is small, then coupling will be maximum for that. So coupling is stronger in BX. So first option is the correct answer. Okay, next one, at room temperature, which molecule has the maximum rotational entropy? Okay, right, and to give answer for this problem, so just to look at the concept here, entropy of a compound related to the number of ways in which molecules can be distributed among different energy states. Okay, right, larger the disorder, larger the entropy. Now we know that the rotational energy is directly proportional to rotational constant B, and B is inversely proportional to moment of inertia I. Okay, and if you look at O2, N2 and D2 and H2, the I and directly proportional to reduced mass, and for O2 reduced mass is more than N2, and that is more than for D2, and which is more than for H2. So from that, moment of inertia, order of moment of inertia can be observed like this, and so it's that means opposite to this order is simply for that rotational constant. Now higher the rotational energy, lower the distribution on excited states, and that leads to lower the entropy. Okay, you can observe that. So this is ground state. Whenever energy difference is small or energy is small, then what happens? Ground state and energy level and excited state will be near to each other. In that case, the states can move easily onto excited state and they can move onto ground state. So whenever that happens, the disorder increase. Whenever disorder increase, entropy increases. But whenever the energy is higher, the excited state is far away from that ground state. In that case, the states cannot and that means the states can't move easily onto excited state, and excited states have less population. That leads to less disorder, and that leads to less entropy. Okay, and in that case, you can see that here BO2, that means rotational constant is highest for hydrogen. Okay, so that's why here the entropy is least for hydrogen. And here in the given diatomic molecules, rotational constant is lowest for O2, okay, and that's why the energy is less for that O2, and that is rotation energy is less for that O2. Whenever energy is small, then disorder is more in that O2, and whenever disorder is more, the entropy is highest for that oxygen. Okay, the answer is O2. Okay, yeah. And next one, the normalized hydrogen atom 1s wave function is given by psi 1s equals to 1 by under root pi. So here we have given with zeta by a0 power 3 by 2 exponential minus zeta into r by a0, where zeta is equal to 1 and energy is minus 0.5 atomic units. If we use a normalized wave function of the above form with zeta not equal to 1, the average value of the energy of a ground state of a hydrogen atom is. Okay, so we have given with this function, wave function, where zeta is equal to 1. Here zeta simply indicating effective nuclear charge. Okay, and for 1s ground state energy, we can use the formula as minus half into zeta square by n square. Here the zeta values for hydrogen is equal to 1.24, helium equals to 1.69, and for lithium we can say it is as 2.69, like that. Okay, right, and just substitute zeta value of hydrogen 1.24, and here n equals to 1 for that 1s orbital, and from that we can get minus 0.8. And but in the problem we have given that energy is minus 0.5 atomic units. That's why minus 0.8 is less than minus 0.5. So third option is the correct answer for given problem. Okay, yeah. Next one, a constant of motion is defined by the equation. So just observe the four options. A constant of motion is a quantity that is conserved throughout the motion. Okay, a quantity is conserved if its Poisson bracket with Hamiltonian is equals to 0. So here Hamiltonian equals to 0 in the second expression. So second one is the correct answer. Next one, the Hermitian conjugate of operator d by dx. So here the adjoint of d by dx is equal to. So whenever we take adjoint of d by dx, it result minus d by dx. So first option is the correct answer. Next one, if y square equals to 4x and 0.1% error is occurred for x, the percentage error involved in y will be. So here we have given with y square is equal to 4x, we can write y is equal to 2 into x power half. So from that the percentage error in y, that is delta y by y into 100 equals to half into delta x by y, delta x by x into 100. Okay, and so here delta x by x into 100 is indicating percentage of error in x, and that is given as 0.1. Just substitute it and we can get 0.05. Okay, the configuration at the two stereo centers in the compound below. So here 1 and this is 4. Okay, so at 1, if you look at 1, so we need to give RS notations. So the first priority for this and second priority, and will goes to here, and third priority for this, and fourth priority for backside methyl group. Okay, so just give the priority direction, it is clockwise direction. Okay, with least priority methyl group is backside, that's why we can say it is R. So 1R. Now look at the fourth chiral carbon. On fourth chiral carbon, first priority will be given for this, because at first carbon double bond is there. And for the second priority, so here CH2, here CH2. Now we need to look for the next carbon. On next carbon we have oxygen, that means bonded with the oxygen. So second highest priority for this, and third highest priority for this. Now just give the priority direction. Priority direction is simply anti-clockwise direction, just like this. Okay, but the fourth priority hydrogen is above the plane. Now we need to take opposite configuration to the direction, because fourth priority or least priority atom is above the plane. So it should be R. Now just give 1R, 4R. So first option is the correct answer. Okay. Next one, the two compounds given below are. So here also just use RS nomenclature on one end. That means two chiral carbons or two fused chiral carbons, and you can get R and S here. At the same time here R and S. So you are getting same RS notations. That's why these two are identical in nature. Okay, that means they are identical forms. Okay, right. Next question. A suitable catalyst for binding out the transformation given below is. So whenever given carbonyl group is going to attack on BF3, here BF3 is a Lewis acid which is ready to accept electron pair. Okay, and just follow the arrows here, and we can produce the given transformation. So the first option is the best option or best catalyst to transform the product here. Okay, next one, the thermolysis of allyl phenyl ether generates. So here just observe the thermolysis of allyl phenyl ether, and we can get artho product only, artho allyl phenyl only. Okay, so 3,3 sigma tropic rearrangement is observed here. Next one, the major product formed in the reaction given below is. So just look at the mechanism here. We have given with Na2CO3 can act as a base and takes a proton from the carboxylic acid functional group. Okay, and in the next step we have given with I2 in presence of potassium iodide. So the double bond makes a 3-membered rings. Okay, and from the backside end. Okay, why it is backside? Whenever we are not predicting any stereochemistry on that, so the given branch should be taken as above the plane. So this is the fundamental thing, and in that case that means 3-membered ring with iodonium should be backside to the plane, and in that case O minus should attack from the above the plane. So whenever that happens, the first option as the correct product for the given problem. Okay, next one, the most suitable reagent for the transformation. So just observe the given 4 options. In that lithium liquid ammonia can reduce that double bond. Okay, right. Next one, the intermediate involved in the reaction given below is. So simply N2 is cleaved as a stable N2 under photochemical conditions, and which result a carbene. Carbene attacked on the given alkene and gives a final product. So option 4 is the correct answer. Next one, in the most stable conformation of trans 1 tertiary butyl 3 methyl cyclohexane, the substituents at C1 and C3 are. So here trans 1, 3 groups must be equatorial axial or axial equatorial in its chair conformation. So the bulk group always should be in the place of equatorial. In that case, methyl group must be axial. So here axial equatorial relation is there, and that is the stablest conformation for it. Okay, and substituents positions at C1 and C3. And next one, among the carbocations given below, just observe the first one is simply considered as homoaromatic in nature, because this sp3 carbon just move out of that particular plane of that molecule, and all the 3 pi bonds make a delocalization and which fulfill all the aromatic rules, and that's why we consider those kind of molecular structures as homoaromatic in nature. And if you look at the second one, which is having delocalization with that positive charge with 2 pi bonds in it, that means 4 pi electrons are involving in the delocalization with positive charge. That's why it is considered as 4n system, and 4n systems are anti-aromatic in nature. And if you look at that aromatic third one, whereas one double bond is delocalizing with positive charge, whereas 2 pi electrons are observed here. So 2 pi electrons, 6 pi electrons, 10 pi electrons are aromatic in nature. Okay, right, that's why the third one is aromatic in nature. Next one, the order of carbonyl stretching frequency in IR spectrum of ketone, amide and anhydride is. So here anhydride the frequency range in between 1800 to 1900, ketone range in between 1710 to 1730, amide range in between 1600 to 1700. Next one, in the mass spectrum of the compound given below, during the alpha cleavage, the order of preferential loss of groups is. So if you look at the alpha cleavage takes place here, and in that alpha cleavage radical formations takes place, and we know that whenever the size increases and branching increase in the radical will become more stable. That's why the first cleavage preference for C3H7 followed by ethyl group and followed by methyl group. Okay, next one, the reaction given below is an example of. So simply just give the labeling on that carbons, and the hydrogen shift takes place from carbon 1 to carbon 5, that is 1 comma 5 hydrogen shift taking place under thermal condition here. Okay, and we know that hydrogen can migrate easily when we compare with methyl group. Whenever the group is small, it can easily migrate. Okay, that's why here hydrogen shift is observed. Next one, the concerted photochemical reaction between two olefins leading to a cyclobutane ring is. So here just see we have two, that means two olefins under through the concerted mechanism producing cyclobutane, and here involvement of foreign system under photochemical condition, simply axial here anthraficial or supraficial addition leads to the stable allowed product. Okay, under thermal condition it should be supra anthraficial or anthra supraficial addition. Right here we have given with under photochemical conditions, that's why it should be anthraficial anthra or supra. So in the option the second one is showing supra addition, that's why second option is the correct answer. Just check the best concept lectures on our pericyclic reactions in our courses. Okay, right. Next one, addition of BH3 to a C double bond C is simply Markovnikov-Zinn addition, whereas the hydride addition onto that more that means branched carbon. Okay, that's why it is Markovnikov-Zinn addition. Okay, right. Next one, the absorption at lambda maximum is 279 nanometer with epsilon 15 in the UV spectrum of acetylene is just due to N2 star transition. Okay, next one, the reaction given below is an example of, just observe the reaction here. Sodium methoxide is a base and which can abstract proton from that carbon, where carbon is directly connected with the strong electron withdrawing group NO2. Okay, whenever carbon ion is formed, that negative charge is stabilized by that NO2. So whenever the carbon ion gets stabilization with that adjacent groups, then that leads through even CB elimination. Okay, fourth option is the correct answer. Next one, the suitable reagent for the following conversion is, just observe here we have given with alpha beta unsaturated ketone, the cyclic ketone, and here epoxidation should be takes place. The best reagent is H2O2 NaOH. Just remember that H2O2 NaOH always makes epoxidation at unsaturation of alpha beta unsaturated ketones. Okay, right. Next one, the relative rates of solubilisis of iodides A to C are. So simply just observe the solubilisis here. The first one where it is producing secondary carbocation, and in the second one is producing vinyl carbocation, and in third one neighboring group participation is taking place. Whenever neighboring group participation takes place, the rate is very high. So that's why C is greater than. And if you look at secondary carbocation and vinyl carbocation, secondary carbocation is more stable when we compare with vinyl carbocation, and vinyl carbocation is least stable. That's why here the rate is highest, second highest for the A, and followed by C. Okay, B. Okay, so the first option is the correct answer for given problem. Okay, right. Thank you very much.